Yeah, Ramba for 2 minutes till the participants are joining. So we will start session in another 1 minute. Okay, please wait. Okay. So in the last session, we have done about physical design, PNR, placement to routing. Okay. So this is how we have completed the last step of routing. So now if we do check design, so this will give you some errors, wrong number of arguments. Okay. So report, what are the congestion area? There is no congestion worse than -2 report. So as it is telling, there is no congestion. Okay. So this is the report for timing. So completely we have the arrival time is 5 nanoseconds and the required time is 39 point something. The required time is 39.984 and the arrival time is 5. So it is having positive slack. So if we have negative slack, we have hold time violations. So this is positive slack time. So we have setup time violations. So setup time violations we can fix very easily. If there are hold time violations, we have to rerun the timing aware placement of standard cells or timing aware, hold time aware routing or hold timing aware clock tree synthesis. So setup timing analysis is always done on or before clock tree synthesis. And after setup timing analysis, they will be doing clock tree synthesis. So after doing clock tree synthesis, we have the actual routing of clock net and other data path nets. So we have hold timing violation. So if we consider an example, I'll explain it here. So this is my ideal time. Okay. If the data is coming here before the rise edge of the clock, this is positive slack. And if the data coming after the negative edge, after the positive edge, okay, or the negative edge, this is negative slack. So what we need to analyze is, if we have a train, bus or flight boarding time is 9 p.m. We have to be there by 8:30 or 8:40. Okay, maximum time. If we are reaching after 9:15 or 9:30, does it meet our requirement? No. We may miss the bus, flight, or train. The same way happens here. The setup time is nothing but if we come here and reach before, we can catch the data when the positive edge of the clock comes. But we need to hold this data here. But whereas after the clock comes or after the bus comes, if we are coming, we may lose our data. So hold timing analysis are very critical. So here setup timing analysis can be fixed by increasing the drive strength of the buffer. Drive strength means here we will, once the data is reached here, okay, we will ask this buffer to transfer this data very fast for the clock rise edge. That is how this buffer works. This is the one of the solution for fixing the setup timing violations. If there is a hold time violation, okay, so what we will do? If it is coming after, what we will do? We'll ask the data to come by negative slack. So we will insert a buffer which will pick up the data at the positive edge of the clock. And one more thing, if it is flip-flop, if it is another flip-flop, okay, to this pin, we have a setup time violation. So what we will do? We can move the flip-flop nearby. This is one of the solution. One solution is buffer insertion. The second solution is moving the two cells communicating each other to the nearby. Or moving the two cells far away to meet the setup time analysis. If you have any questions, please post. Ramabu, my audio is clear? Screen is visible? What I am explaining? Tarak, Bhuneshwari. So there are very less number of participants. Okay. So there are two types of timing violations. We have setup timing violations and hold timing violations. Okay. So if the required time is more and the data reaches very fast, then we have setup timing violation. It should be nearly 38 or 35. But the data is coming too early. So what we will do? We will increase the delay in arrival time. So just I am reading the report of my design and explaining you what is the timing violations we have. Rohit, we have two properties for the buffer. So in the library, we will be having different types of buffers where the buffer can increase the delay and we have some buffers which can decrease the delay. So that means the buffer drive strength is very high. That is to reduce the delay. If the buffer drive strength is very low, that will increase the delay. Got it? Rohit, there are two types of buffer cells or standard cells. We can increase the delay and we can reduce the delay. Both are the properties of the buffer. And if you have the whole timing violations, the net length is more. So what we'll do? We'll try to reduce the net length so that it reaches in time to the rise edge of the clock. Yeah, buffers are all type of buffer. We have two terminal buffers, three terminal buffers, tri-state buffer, any kind of buffer, Sharon. Okay. So whatever is available in the library, we'll pick it up and we'll put it in the drive stage, whether it is setup fixing or hold timing fixing. Sharon, we can use tri-state buffer also. So if you are using tri-state buffer, okay, so you need to give the select fit. That's it. So report underscore area. So the total area of the die is 1160.28 square mm. And the instance count. Instance count means number of cells, that are 143 cells. Just I have the instance count of 143 cells. Got it? So the power report is very large. We will analyze here. So the total internal power is 77% and the switching power is 22% and the leakage power is 0.1 or 0.2%. Okay. So we are if you see, there are no macros, there are no IOs. Okay. Sequential logic cell is having 73% of power consumption. Internal power is this much, 0.032226 watt, microwatt. And switching power is this much. Leakage power is this much. And total power consumption is this much. So combinational logic and clock logic. And out of 100, so this much is the total power consumption. Next is rail, power rail. How much power rail has to consume? it has to consume voltage of 1.2 volts. I am supplying it 1.8 volt. So it is receiving only 1.2 volt. So there is IR drop. So where is that IR drop? I need to check. And clock percentage is 20.70. So out of which the leakage is 6.80. Those all are in microwatt. Okay, units you can see in the top. Power nets we are giving VDD 1.2 volt, VSS is 0 volts. Which tool is analyzing the power? Voltas. Voltas is the inbuilt tool in the Innovas, which is calling the functionality for power analysis. If it is for timing, it will call Tempus. For power, Voltas. Okay, these are the two specific tools from Cadence. So if you see the design, it looks like this. So these are the standard cells. So these are the base layers connectivities for the standard cells. And this is the routing. So this is routing net. So this net is communicating till here to the data pin of my logic cell. And it is also connected to the another data cell here. So this is one standard cell and this is another standard cell. So all these two standard cells are connected to a single net and it is reaching other logic in the receiving. Is this clear, everyone? The previous session it was stuck, so I didn't disturb it, so it completed the routing part. Correct, yes, thank you. So give me 2 minutes, I'll open the presentation. Hope my screen is up. So we'll try to run a design using analog circuit. So this is analog circuit design tool from the Cadence, which is Virtuoso IC 618. So, so this is tools library manager. So in the library manager, we have the technology libraries and other libraries also. So I'll show you what is the technology library and how it looks and what are its features and how are the standard cells. VLSI 65 LL. So this is the screen is the font is very too less. Okay. Try to zoom in and observe on the presentation. Okay. So we have different kinds of devices. This is PDK, process design kit. So if we check, we have diodes, we have capacitors. Okay. We have NMOS transistors, we have PMOS transistors and other operating sources of voltages and current. So suppose if I want to design an inverter, so what will be my procedure using the cadence tools? Exit. So file, new library. So first I need to create a new library. That is nothing but technology dependent, our own inverter design. INV 29. Correct. Attach it to the existing technology library. So what is my technology library? UMC 65 LN. File new library. The tool is working. So NV June 29, I'm designing a new library. After creating my new library, it will take some few configuration files. So from this, I have to pick one library, EMC65 LL. So I'll check here what is the technology library they have attached here. EMC65 LL. Okay, once we have attached the new technology library, so everyone is able to follow the steps, please. Okay, so this is analog design flow. So far, what we have done, we have completed the digital design flow. So now we are using directly the tool. There is no theoretical concept. Directly we are going to the theoretical concept to design the analog circuit. Is everyone able to follow? View the screen? Understand? If you have any questions, please post it. Dear participants. Yes, sir. Thank you. Next step is click on import Verilog for importing the Verilog code to attach to the existing. Next in the CIW window, file, click on import Verilog. Okay. This is safe side for me. Import. In that import form, it is a Verilogin method. So in that Verilogin method, we have to load the Verilog file. RTL. So I'm using divided by 2 circuit. Okay. Target library name. Library with precompilation HDL. Click on OK. So Verilog in file is completed. So there is no errors. So we'll close this log file. Next is create new test bench, new cell view, test underscore the cell name is TB underscore view underscore view. And I'm using schematic here. We want to overwrite it. We'll go to number one. So we generate a test bench. So in this, add instances. Click inside this I library. Symbol and file. So this will give me the cell. Next, I have to press escape. This is my divide by 2 clock circuit. So I have written a Verilog code. I'll try to open that Verilog code and show you. Here. So this is the behavioral modeling of coding. So in this, I have written a code module divided by 2 clock. So I have a clock, the reset, output, and clock. So clock is the input and the out underscore clock is the output. The out underscore clock will be divided by 2 and come out. So how it will divide? That is how we are writing the logic. Always at the rate positive edge of the clock or negative edge of reset. Okay. If not of reset, out underscore clock equal to 0. Else out underscore clock equal to negative edge of clock. So how the clock will be defined? It will be so this is my one duty cycle. This is my another duty cycle. Okay. So this is I am generating using the Verilog. Clear? So for everyone, understood? For this Verilog code, I am creating an analog test bench. So previously what we have done, we have directly written a test bench using Verilog code. So if you want to go for mixed signal or analog mixed signal design, okay, for that we have to use Verilog code and digital circuit and analog circuit. So for that reason, we will be using analog and mixed signal design. So for this, I am creating a test bench. So now I have got the test bench. So for this logic, I have to create a test bench. Add V2 pulse instances and give the parameters. and a log lip, V pulse, you will give you the edit object properties. So in this edit object properties, 1 second. So we are adding the voltage sources. So this is how the test bench will be created. So this the tool is lagging. So I have created the test bench. So I have connected a pulse of duty cycle. Okay. And this is for input, and this is for reset, and this is for sourcing. So using these, we are running the simulation. So how we will be running the simulation, I will explain. launch ADL. So nowadays ADL is not available. So we have to go for assembler and explorer. So there is a lot of okay. So next is setup simulator. So we have to go for analog mixed signal AMS. And we need to choose the sim directory path. Yeah, Ganesh, please tell me what doubt you have. Sir, once show the test bench code. So there is no test bench code. So this is how we are creating the analog test bench. So what we are doing is, so in digital, what we will pass? We will pass for a divide by counter clock signal, reset #100. Okay, I'll write and show you that code. Okay, 1 minute. So it's giving an error. So directly I'll try to open the config. Yes. Till it is not taking. Next session, load state. Yeah. So once the data is loaded, we can click the green button to run. Not sure if the full license is old, we may get the result of. But I'll try to explain you the digital test bench along with the analog test bench in comparison. How does this works? So if we see the timing diagram, okay, this is 1 clock pulse. What we are asking? We are asking it to divide the clock. So what it is doing? It is dividing every 2 clock pulses to 1 clock pulse. So now I'll explain you the theory behind this circuit simulation. Okay. So this is the test bench creation, and this is your very log code. I'll put a small note. I'll put a another small note. Explain. So what I am trying to do, we write a Verilog test bench. What we'll do, we'll pass the values in the test bench in this way. Hash 100. Okay. Result equal to 0. That means not of reset. If reset is 1, it will give you the output clock equal to 0. And if there is reset is, if this is 1, okay, and if the result is 0, then it will go to output equal to negation of the clock. So hash 10 out underscore clock hash 10 out underscore clock. So in this way, I'll be giving the input delay for every 10 units of time. Here I am declaring the delay. This is how we create a digital test bench. So in the same way, I am creating a reset signal. I am creating a voltage source here, and I am creating a pulse. So for every 10 units of time, sorry. So for every 10 units of time, I am creating a clock. This 10, the initial delay. So this is the duty cycle. Rohit. And another 10 is this one. So this we are passing using these. This is voltage source or V pulse. So if I click and check the properties of this circuit, okay, I am giving a pulse. The period is 1000 microseconds. And the delay is 100 nanoseconds. And rise time is 20 picoseconds and fall time is 20 picoseconds. And pulse width is 70 microseconds. This much we can define in analog. Analog is very accurate than digital. So the pulse width is, Rohit or other students, please understand here. We are defining the period. Period is 100 microseconds. One clock period is 100 microseconds. And the delay time is, to start this clock period, the delay time is 100 nanoseconds. Okay. The rise time is 20 picoseconds. This rise time. The clock rise time is 20 picoseconds. And the fall time is 20 picoseconds. And complete clock period is 100 microseconds. Everything will be in micro, nano, pico, okay, or femto. The pulse width is 70. And each and every pulse width is 70 microseconds. So combining all this, I'm generating a clock, which will have zeros and ones. The same way, we are generating the clock here in the timing diagram. So this is the input signal. Once we have the reset close, then the output of clock is divided by 2. Got it, everyone? Here. Exactly here it is dividing the clock by 2. And it is given 1 clock cycle. Clear, everyone, so far? Understood? You are able to catch the things? Using Verilog, we are doing a analog mixed signal simulation. Reset equal to 1 mean out means out is equal to negation of out. Correct. So reset should be high. This is active high reset and active low reset. We have two kinds of things. So we have to define in the code whether it is active low reset or active high reset. Got it, Rohit? So we are working on the active high reset. These are in detail terminology. So pink color line is the output clock. Green color line is the reset. So when the reset is happening, okay, it is on the negative edge of the clock. So what it has to do for the next positive rise edge of the clock, it has to divide the clock by 2. Rohit, you are getting. So it's all your functionality, whatever you write. How you want to define the code or how you want to define your test bench. So it depends on the circuit design engineer, how you want to meet his functionality. Rohit, you are able to catch? Okay. Anyone else has doubt? Clear so far, everyone? Nice. Any doubts? Please let me know. Bhuvaneshwari, you have any questions? Yeah, we have to run that clock, but I am not running that clock continuously here. I am dividing only it at once. If I want to run the clock, I can run it for a pulse of time. Okay, but I'm not running the pulse of time. Rohit, you got it? I just need to divide the clock at once. Okay. So it's all design specifications. So how we want to design, how we want to define, how we want to run, and all those things. So we have learned few things in these tools. Okay, using digital, we have done Verilog code verification using digital test bench, and we have completed full cycle of asset design flow. And second thing is using analog circuit design, we have imported digital Verilog code, that is divide by 2 clock circuit. So using this clock or using this Verilog code, okay, we have designed a analog test bench. So analog test bench can be designed using ADL, analog design environment, ADEVs. So using that, we have simulated the test bench. Hope this is clear so far today. Got everyone? Yes. So I don't have the tool access licenses now. So I'll just walk you through the other slides for the analog flow. Give me a second. I'll just walk you through one more design setup. That is analog mixed signal design setup. Okay. So yeah, continue.
So good evening, sir.
Sir, good evening. Continue.
Okay,
What
sir.
will
Thank
you
you, sir.
Okay.
Sir, I'll tell about the custom compiler using the C.
Yes, yes. You just brief them about the inverter
Okay,
characteristics and custom compiler. Okay,
okay, sir.
how they are going to use the custom compiler operations or options. But
Okay, sir.
you have that, do you have the tool access? No, right?
No, sir, it is licensed, so I don't have a tool, but I have the PDF about the explaining of the CMOS inverter in custom compiler.
Yes, yes. Please do proceed. Sure.
Okay, sir. Thank you, sir.
Okay, thank you. So Sharath will take up the custom compilers, CMOS characteristics of inverter. Okay. So I have some medical emergency, so I am right now to go. So Sharath will continue the session. So please take participants attend to the classroom. So based on the questions, I'll give you the assignment about CMOS inverter characteristics. It is very interesting and very learning. There is a lot of subject to learn with the tool also. Okay. So if you have the tools at your campus as Bhuvaneshwari or Tarak They are having the tools in the campus in their engineering colleges, so they can experience this kind of things experimentally. Okay, sure, continue. Thank you.
Guys, good evening all. Could you able to hear my voice? Can you please respond in the chat? Yeah, okay, thank you. As you all of you know about the CMOS inverter, uh, going to explain about the CMOS inverter, how we should create the CMOS inverter in the custom compiler. I'll share the screen. Wait a minute. Yeah, are you able to see my screen? Okay, thank you. As you all of you know about the CMOS, CMOS is a complementary metal oxide semiconductor. Uh, it is a combination of a PMOS and an NMOS. Uh, as you see the circuit diagram of the CMOS. Yeah, it is a just simple. When we give a high input to the CMOS inverter, it will give a negation of the input. If we give the high input, it will give in the output low output. And if we give the low input, it will give the high input. It is the basic uh, formation of a CMOS inverter. As all of you see in that circuit diagram, uh, I'm going to show you how we construct a CMOS inverter in the custom compiler. So basically, it is a licensed one. So I don't have a license in my laptop. So I'll show you how we construct the CMOS inverter. Yeah, once you open the custom compiler, we'll get this pop-up. In this, we are going to open the library manager, uh, as you see in this. So we should always give the library. Yeah, Chandana, what is your doubt? Could you please respond in the chat? Chandana. Yeah, okay, leave it. So firstly, we are confirming the libraries what we should use in the custom compiler. We'll use the SAED 90 nanometer PMOS and NMOS in this. We should also use the 14 nanometers and 90 nanometers in this custom compiler. So firstly, we have to create a library. I'm taking the library name as inverter, CMOS inverter. So I'm also giving the directory name as well, the same inverter. So we should enter the SAD 90 nanometers. So we should give the library names to the PMOS and NMOS. So as we are constructing the CMOS inverter, so these steps you have to follow first. So firstly, you have to create a directory and you have to give a name as CMOS inverter. Yeah. Then you have to create a cell view, as you can see. So the cell view is basically gives the structure of the PMOS and NMOS. So I'm giving the cell view name as the same inverter. So we are going to create the schematic of CMOS inverter. So firstly, I'm taking the PMOS. So firstly, I have to give the PMOS the high end. So I'm connecting it to VDD. So firstly, I'm going to show the schematic. Yeah. Before that, we have to go into the technology manager. So once you right click on this, one window will pop up in the software. So you should give the technology to it. So I'm giving us SAED 90 nanometers as here you can see SAED nanometer for PMOS and NMOS when you're constructing the CMOS inverter. Yeah, these are the this is the PMOS and this down one is the NMOS. So firstly, I'm going to construct the schematic of the CMOS inverter. Um these are all the length and multiplier lengths are also fixed in the software and the custom compiler. You don't need to add any length or multiplier as editing instance parameters. So once you go into the schematic, this is the schematic of the CMOS inverter. So you can see here, wait a minute. Yeah, this is the PMOS and this is the NMOS. Are you able to see my annotation? Could you please respond in the chat? Are you able to understand how we gonna create? Okay, thanks, Chandani, thanks, Monica, Bhargavi. Yeah, Ram Babu, thanks. So firstly, we are constructing, once you go into the instance, as you have seen in the Cadence Innovus. So firstly, I'm going to start with the instance. When you press the I in the keyboard, you'll pop up with the window instance. So in that, I'm going to give PMOS 4 terminal. So I think you all know about the NMOS, how the MOSFET is used to be. Basically, it is a 3 terminal. You can see. Can you please tell me in the chat what are the three terminals of the MOSFET? Can you please respond in the chat? What are the 3 terminals of the MOSFET? Yeah, you're correct. Source, drain, and gate. So these are the 3 terminals, but we are using in this custom compiler the fourth terminal. The fourth terminal is the body. You can see substrate. So I'm taking the NMOS and PMOS. So firstly, I'm taking with the 4 terminals. You can see here red dots. The upper one is here. The upper one is this is gate, and uh, yeah, you're correct. Arati, gate, drain, and source. So this is the body, and this is the gate. You can see here drain, and this is the source. So I'm connecting the 4 terminals to each 4 parameters. In this PMOS, I'm connecting this source to the VDD terminal, and this body also to VDD, and this drain is to Vout where we can get the output. And I'm taking these two inputs of PMOS and NMOS to what we are giving the input as 1 or 0. We are connecting to V pulse. So this V pulse will give the input as 1 or 0. We can make the input as we want. So I'm also connecting this PMOS to VDD and this NMOS to ground. So why we are connecting to PMOS to VDD? Can you please uh, mention in the chat? As you all know about the PMOS and NMOS, uh, we call PMOS as a pull-up network and NMOS as a pull-down network. Why we call PMOS as a pull-up network and why we call NMOS as a pull-down network? Can you please respond in the chat why we call PMOS as a pull-up network? Anybody knows why we call PMOS and NMOS as follows: pull-up network or pull-down network? Bhuneshwari, someone. Majority holds no, no, it's not correct. PMOS produce strong logic. So when PMOS produce strong logic one, why PMOS produce strong logic one? Yeah, it's correct. Satya is correct, and Bhavani is also correct. So it's basically PMOS. You can see PMOS charges the capacitor, this capacitor up to VDD. So it produces the PMOS, the strong logic one, and this NMOS. You can see here this NMOS. This discharges the capacitor to zero. So we call the discharging part as pull down network, and the charging part of PMOS as a pull up network. Yeah, you're all are correct. You're not up to the point, but you are correct. Did you understand why we call pull up network and pull down network of PMOS or NMOS? So basically, PMOS charges the capacitor to VDD, and the NMOS discharges the capacitor to zero. So that we call pull up network and pull down network. So here we are connecting the PMOS to VDD and this NMOS to ground. So here we are connecting VDC. So we are giving 1.2 volts. Is this capacitor has 1 Faraday. V-pulse has a characteristics. I'll show you how to give the V-pulse inputs and outputs. I'll show you. Okay. Okay. Yeah. Okay. So firstly, we are creating the schematic. Is anybody having the doubt with the schematic? How we connect the CMOS or somebody is asking? Please repeat once about the pull-up. Yeah. Uh, Dumati. Yeah. I'll repeat it again. So firstly, the CMOS consists of PMOS and NMOS. Wait a minute. Yeah. So basically, we'll give the PMOS and NMOS in the CMOS inverter. PMOS will connect to the VDD because PMOS will charge the capacitor up to VDD. So it produces the strong logic one when we connect it to VDD. So and NMOS will discharge the capacitor up to zero. So that we call NMOS as a pull down network and PMOS as a pull up network. I think the doubt is clear, Indumati. Is the doubt clear? Yeah, okay. So I think all of you are clear with the CMOS inverter schematic. So we'll go to the next part. So we have created, so firstly, we are given the library instances to the CMOS compiler. So basically custom compiler. And then we created the cell view and then we created the CMOS schematic. Then we have the 5 steps to follow. Firstly, I'll show you how to run the module. So firstly, you have to go to the here file part. I think it's not visible up to the mark, but you can see here. Firstly, we should go to the prime wave design environment. Yeah. Before that, I'm showing the VPulse and VDC component parameters from. You can see here. This is the prime wave. Is the prime wave component. You can see here. Firstly, we should give the voltage as 1.2 and then rise time as 0.2 milliseconds and the fall time 0.2 u and pulse width 2 u and period time 4 mu u. So you have only here you can see there is only one V pulse here, so that you are giving 2 and 4. If you have any other 2 or more V pulse, you can give as 3, 6 and 4, 8 milliseconds to the pulse width and period. For all V pulses, you can see rise time and fall time as 0.2 u seconds and voltage 2 as 1.2 u, 1.2 V voltage. So it's all constant uh, constant you should give to the vpulse. And here in your right you can see the vdc. So firstly we are giving dc voltage 1.2 volts. That's the constant value we'll give to it. uh, Next we are going to see how to run this module. Okay, you should go to the prime wave design. It should be in the left side of your terminal. Then we can see the IDVGS or IDVDS of CMOS. How we'll get the, you can see. So when you go to the prime wave, you can see we have a DC analysis and a transient analysis. You can see in the analysis type. You can see here there is a transient here in DC. I'm taking the DC. You can also take the transient analysis. So here you should select the sweep button. Then these window will pop up. I'll show you by annotation. These sweep button. This window will pop up. You can select the sweep variable as design variable and variable as Vx. So this type is also PRM and sweep range up to 0 to 1.2 volts. So when we are giving the ID VGS graph, so how will be the ID VGS graph of uh, MOSFET? This is the ID VGS. This is the, yeah, the current ID. Yeah, you can see. So we'll start from 0 and end up with 1.2. We'll sweep from 0 to 1.2. And this is sweep type is always linear. And you can take the number of step as 20, 40, 30. That's your wish. That's not a problem at all. Then next, you're going to the variable. So you should select the Vx as 0 0.2 here. 0 0.2 Vx. Then you should select the library files from the custom compiler. So you should include the path SID 90 PDK HSpice. So you have a library files. This is libbis libtype technology files as library files. So you should select the technology 90 nanometers. So when you include the path of SID 90 nanometers library, so you should select the section as TT 12. It's the constant value in the prime wave selector. This is the second step, and this is the third step. The simulation part, you don't need to select any change from the simulation part. You should just click the simulation and click OK. And you should click the prime wave, HSpice, and here accuracy level as 4, and you should take the number of processes as 4 steps. This is the constant values in the custom compiler. uh, and you should take the output and input node voltage plotting. So so after this you should select the values. You should select the lines from the you should select the voltage input and output from the schematic. So once I'll show the schematic. So you should select the V in and V out as the expressions from the schematic. So once you press the expression button from the module, here you can see, I'll show you. Yeah, here you can see this is the V in and this is the V out. You can see here. Yeah, this is the V in and this is the V out. We are selecting from the schematic. So here we are taking only DC plot. So how will get, yeah, this is the output of the DC. So you'll get like a VTC curve, voltage transfer characteristics curve. You can see here. So this is the voltage transfer characteristic of a CMOS. So there is a pure drama in selecting the VTC curve. As you all, I think you have known about the VTC curve, VTC plot. Can you please respond in the chat? Is anybody know about VTC curve, how it is formed, and how we can draw the VTC curve? Anybody from the chat, please respond. No idea. Okay. Wait a minute. I'll show you. Yeah, all of you, can you please respond in the chat? My screen is visible or not? Is it visible? Yeah, okay. So this is the CMOS inverter voltage transfer characteristics. So firstly, how it is formed. You can see here a CMOS inverter. So we are taking the plots of voltage of CMOS and NMOS, whether it is in linear position, whether it is in saturation position, or whether it is in uh, off position. So firstly, you can see here, these are the VTC operating regions. You can see here. So firstly, we are selecting A, B, C, D, E. These are the five regions of NMOS and PMOS, whether they are in different positions. So in A positions, you could see NMOS is in saturation position and PMOS is in off position. So we can see here, we are plotting a graph from the NMOS and PMOS, how they are acting in different regions. So I'll show you how it is. Yeah, you can see here in the A position, the NMOS is in off and the PMOS is in resistive. So resistive in the sense these are linear position. Uh, yeah. Okay. So in the B position, NMOS will get into the saturation and PMOS will in the linear as usual. So at the point of at the point of C, you could see here, yeah, here in the C position, the NMOS and PMOS both are in saturation regions. So we call it as switching threshold. So we call it as VM. So VM in the sense, VM is the point where V in and V out are equal. So we could see in experimental values and the theoretical value. So theoretical, we could say V in equal to V out. In the experimental, so once you get the VTC curve from the point of origin, you could draw a line where this line is 45 degrees. 45 degrees. So where the point intersects the VTC curve, this point is called switching threshold point, where NMOS and PMOS is in the saturation region. So at the point of D, NMOS is in the linear position and PMOS is in the saturation position. So at the point of E, NMOS is in the linear position and PMOS in the off position. So the VTC curve shows the uh, positions of the working casuals of NMOS and PMOS, how NMOS is starting with off and concluding with PMOS getting to off position. When you are giving a input from low to high or high to low, you could see here, this is the working of VTC curve. You could all see, yeah, we'll go to that slide. Yeah, okay. So this is the VTC curve. It is formed like this. So it is a DC of the VTC curve. So once you get this VTC curve, so you should give a tangent value to it. So once you go to the uh, measure, there's an option called measure. It will calculate the all the V in and V out and VOH and VOL. So output low to output high. So once you select the signal, you could give it would give the tangent value, could give the slope equal to -1. So once you give the tangent value, here also we are giving the same. So it should when you ungroup the both values, you'll get the graph like this. You could see here. Yeah, this is the DC curve of the CMOS inverter. So once you go into the transient analysis, so in the simulation part, once you choose the transient analysis in edit analysis window, So we are also putting the start time as 0 and set the time step to 2 mu to 30 mu here in the sense. So firstly, in the DC case, we have taken the DC part. So we are taking now the transient part in it. Yeah. So we are dealing with the transient analysis now. So how the PTC curve will come in the transient analysis. So once you deselect the DC sweep and change output analysis to DC transient mode, you'll get the window like this. So here you can see there is no DC. We are dealing only with the transient part. So we are taking the same 5 steps in that. So we are taking the expression as V in and V out. So we are going to simulation and netlist. So you could choose the option in the window netlist and run, or you could see shift X and control R. You could so the netlist part is shift X, so it will give the errors or something in the uh, any of the errors in the simulation part or in the schematic part. It will give the errors if it has any errors. So if we press the control R, it will run the module. So this is the transient analysis waveform. You'll get like this. So if we give the input 1, so in this you can see the input is 0, we are getting 1. So here your input is high, the output is low. This is the transient analysis of the CMOS inverter. Yeah. Is anybody having the doubts on this module? Can you please respond in the chat? If you have any doubt in the about the CMOS or the simulation part or something. So I'm not aware of Vivado. I think these Vivado is for cadence innovers where we are using the Verilog code, but we are not using any of the code here. But just we are using the instances and we are creating the schematic of CMOS inverter and we are running it. Uh, yeah, no, no, sir. Okay. So I think Chaitanya sir has also informed, like explained about the cadence innovers and the working part of this CMOS inverter. So I just explaining about the custom compiler, how it works. It is truly uh, interesting when you do the CMOS parts and the custom compiler. If anybody having any doubts, can you please respond in the chat? Otherwise, I'll put the attendance link. Yeah, Indumati, what about the projects? So I think the Blackbucks team, have you given any projects about the Verilog projects? They informed about the projects, or they said they will inform you about the projects. I think they're not informed you about the projects, but they will give you the projects after 7th, I think so. You'll be working on the Verilog codes about different. They are also simple Verilog codes. They'll give you on 7th, I think so. We are working on the projects, Verilog projects. They're also interesting projects. You'll do from 7 to 15th, I think so. They'll inform you, I think, so, Indumati. Anybody has any doubts about the CMOS inverter or custom compiler? Can you please respond in the chat?